Swayam Prabha. Digital India. Educated India.
In the problems that we have been solving so far in dynamics, we have been working in inertial frames. By inertial frames, we mean those frames of references where no acceleration is possible without an applied force. As I have commented in the past, this of course is an idealization. On the other hand, it is sometimes useful to work in non-inertial frames. Where you would see that particles are accelerating without an applied force. The reason for working in non-inertial frames are twofold. Number one, that it makes solution of a problem easier in certain situations. And two, as I already commented, the inertial frame, idea of inertial frame is an ideal one, and most in real life the frames are non-inertial and sometimes their effect is measurable. And for example, the earth, because of its rotation, is a non-inertial frame, and therefore it has effects that are measurable and that are significant. So for these two reasons, we will now work on how to solve problems in non-inertial frames. We will be considering two kinds of frames. One, a uniformly accelerating frame, and two, a rotating frame. How an acceleration can arise in such frames without an apparent force can be seen if you see a frame which is a uniformly accelerating frame. Suppose you are in a car which is accelerating in a particular direction with acceleration a. As it is moving, you will be seeing other things outside car accelerating backwards, although there may be no force on those, but you will see them as if they are accelerating backwards. And therefore you see qualitatively how sitting in a non-inertial frame or in a uniformly accelerating frame, you see things accelerating past you but without any force being applied on them. We want to solve problems in these frames applying Newton's second law. That states that force equals m times the acceleration. Therefore, if you see things accelerating without any apparent force, to account for this apparent acceleration, you have to introduce certain forces, and we call these forces the fictitious or pseudo forces. For example, if you are sitting in a uniformly accelerating frame, you will have to imagine as if there is a force pulling things backwards, opposite in the direction in which you are accelerating, and that would be a fictitious force which is equal to m times a. Let us see this quantitatively. Suppose there is a fixed inertial frame, let me call this x prime, y prime with origin at O prime, and let us have another frame which at time t equal to 0 is coincident with these axes x, y with origin O, but this frame is accelerating to the right with an acceleration a. If that is the case, you can write the transformation equations as, after time t, what you would see is that the original frame is fixed where it is, but the accelerating frame has moved forward by a distance of 1/2 a t square in time t, and therefore you can write that x would be equal to x prime minus 1/2 a t square, y equals y prime, and if there is a z axis, z equals z prime. Therefore, for a particle being observed in the two frames, x double prime would be equal to x prime double dot, that is the acceleration in the accelerating frame would be x prime double dot minus a. Y double prime would be equal to y prime, y double dot will be y prime double dot. So, you see acceleration in the accelerating frame has decreased by an amount a. If x prime double dot is 0, that is the acceleration in the fixed inertial frame is 0, you see that x double dot is equal to minus a. That is, you will see things moving past you, accelerating backwards. And the way we explain it, as I said earlier, is by introducing a pseudo force. Let us see how that comes about. So, just talking in this one dimensional case, x double dot, which is the acceleration in the accelerating frame, is equal to x prime double dot minus a. If I multiply both sides by m mass, this is m x prime double dot minus m a. This, recall, is the true force F applied, because x prime double dot is the acceleration in the inertial frame. So, this is real F applied force in the x direction minus m a, and therefore, the acceleration in the accelerating frame I write as F applied minus m a divided by m. This entire thing is like a new force which is calculated by F equals F applied or external minus m a, which is a fictitious or a pseudo force introduced to account for this kinematic effect. The kinematic effect is because I am sitting in a frame which is accelerating, I see things accelerating past me for no apparent reason. So, reason I attach is I introduce a force, and now I have got my equation of motion, and that is that in the accelerating frame I would describe the change in the x coordinate as F in the x direction applied minus m a, and that should solution of divided by m. Solution of this should give me x as a function of time. In general, let me write r double dot in the accelerating frame as F in the accelerating frame, F external or F applied minus m a vector, where a is the direction of acceleration of the uniformly accelerating frame divided by m. This is going to be my equation of motion in the accelerating frame. I emphasize again, the force that we have introduced m a is a pseudo force. It does not exist in nature, but we feel as if things are accelerating past, so we introduce this force, and solution of this gives r in the accelerating frame as a function of time. One comment about this pseudo force that we introduced, minus ma, it is like gravitational force on the surface of the earth, except that its direction is slightly different. Recall that if I have a body on the surface of the earth, all parts of it are pulled towards the earth by a uniform acceleration g. Similarly, in this case, if I observe an object from a frame which is moving, say, towards the right with the acceleration a, all the parts of this body are accelerating backwards with the same acceleration a. So, it is as if the body is an effective gravitational field with gravitational acceleration minus a. Just like the force out here, the net force in this case acts on the center of gravity, which we call the net force is mg, and it acts at the center of gravity. In exactly the same manner out here also, since the force is uniform acceleration for each particle, it will also be acting on the center of gravity towards minus a direction, and the total force would be ma, minus ma, but it will work at the center of gravity. So, that is a sort of similarity between the pseudo force observed in a uniformly accelerating frame and a gravitational force. The way we can use this fact that things in an accelerating frame appear to be being pulled by a gravitational kind of force, we can use them to solve problems in much easier way in certain situations, and this I will best illustrate through examples.